we present MeshNet++, a network with a face. Triangular meshes are popular in multimedia applications. They provide a natural delineation of complex 3D shapes. Flat surfaces can be represented with a few larger triangles, and large smaller triangles can portray intricate regions. Shape analysis of meshes in deep learning frameworks is non-trivial. Meshes are irregular as they consist of a varying number of mesh elements. Meshes are also complex. For instance, an input unit to a neural network can be its vertices, edges, or faces. MeshNet++ is a novel deep learning network composed of multiple blocks. It first learns spatial features from mesh faces. The spatial descriptor generates spatial features from the center points of mesh faces. The structural descriptor consists of the face normal descriptor and the spatial correlation blocks to measure the appearance of and around mesh faces, respectively. A key contribution of MeshNet++ is its surface correlation blocks. They capture local structures as directional vectors from the face centers to the surface points on neighboring faces. To constrain the surface points on neighboring faces, MeshNet++ samples the points either under a multinomial probability distribution or uniform probability distribution. Compared to multinomial sampling, an equal number of points are sampled from neighboring faces with uniform sampling. Surface correlation blocks then learn kernels of directional vectors to jointly respond to the captured directional vectors based on cosine similarity. The surface correlation blocks in MeshNet++ capture local structure at multiple scales. A higher scale implies a larger neighborhood further away from the face. MeshNet++ concatenates features from the spatial descriptor, the face normal descriptor, and the surface correlation blocks at multiple scales. The resulting feature is more comprehensive as it contains both spatial and structural information. This feature is passed on along to the mesh convolution block. Mesh convolutions in MeshNet++ are performed on a single dimension. To further improve the information flow, we propose a mesh convolution block. The mesh convolution blocks follow a dense connectivity pattern. We introduce direct connections from an initial mesh convolution to all subsequent layers. These features from mesh convolution blocks can be considered as the global state of MeshNet++. This is because all succeeding layers have access to all preceding features. Pseudo mesh pooling performs pooling operations on meshes. Unlike other approaches, pseudo mesh pooling does not downsample the resolution of an input mesh by decimation. Instead, downsampling is achieved by carefully eliminating a few faces from consideration in the succeeding layers. For this, the mesh convolution block operations are conducted on the faces of the farther and larger neighborhoods without changing mesh connections. Features are repeatedly processed using sequentially stacked mesh convolution blocks and pseudo-mesh pooling blocks. After the final mesh convolution block, max pooling is applied across the spatial dimension to obtain global features for a mesh. Global features are fed into an MLP to get classification scores. We evaluated MeshNet++ towards mesh classification. To this end, we first determined values of MeshNet++ hyperparameters that would generalize across multiple datasets by performing an ablation study on the Shrek 11 and the ModelNet 10 datasets. We also find that using multiple surface correlation blocks is beneficial to the classification performance. The MSB dataset offers a repository of 3D models with articulating parts. MeshNet++ outperformed other state-of-the-art methods in classifying this dataset. Split 16 of the Shrek 11 dataset has 16 models for training and 4 for testing. MeshNet++ achieved 100% accuracy on this split. For all 30 classes, Split 10 contains 10 models to train and 10 for testing. Compared to Split 16, accuracy drops for all methods for Split 10. MeshNet++ again outperformed other methods on the cube engraving dataset. View-based and point cloud-based methods are prevalent in analyzing the ModelNet 40 dataset. However, in recent years mesh-based analysis of ModelNet 40 has gained traction. ModelNet 10 is a subset of the ModelNet 40 dataset. MeshNet++ gave the highest classification accuracy on this dataset compared to the other listed methods. The 3D future dataset exhibits high intra-class similarity. The fine-grained classification of meshes in this dataset is challenging. However, MeshNet++ gave the current state-of-the-art accuracy on this dataset. The surface correlation blocks capture the appearance of the local structures around mesh faces. We qualitatively verified that these local structures got captured as expected. Faces in these meshes were highlighted with different depths of a single hue. The depth of colors corresponds to the value of features in a channel. We observed that the faces in each mesh exhibit distinct activations for different channels of a surface correlation block. These distinct activations are expected since each channel represents a directional vector's maximal response to local face neighborhoods. We also qualitatively verified the effectiveness of capturing local structures at multiple scales. For a surface correlation block at a particular scale, faces of a mesh located in similar appearing areas produced identical activations. Also, activations exhibit higher similarity at a lower scale of surface correlation block and vice versa. Finally, we visualize the kernels of surface correlation blocks at different scales across different datasets. It can be seen that the distribution of directional vectors is biased towards specific directions. Therefore, adding more kernels and combining them could improve the performance of MeshNet++.